This organic chemistry video will focus on Chapter 13, Ethers and Epoxides. And we're going to be working on Activity 4. So first of all, epoxides can be made from alkenes in a sin-selective manner and by either of the following reactions. So as we can see here, alkenes, when treated with MCPBA, which stands for metachloroperoxybenzoic acid, we form this epoxide. It is important to notice that the substituents at either side of the alkene stayed in the same plane, and that's because they're in a cis conformation. Now, MCPBA, when using MCPBA, we also get its enantiomer. When alkenes are treated with Br2H2O followed by NaOH, we also get an epoxide. And once again, because the substituents at either side of the alkene are cis to each other, the substituents at either side of the epoxide are in the same plane. Provide the substrates and reagents needed to synthesize the following reactions. So how I like to approach these kind of problems is, we're given the product, so if we have an epoxide, we have to remember that it comes from an alkene. So we can just redraw a line here to remind ourselves that it came from an alkene. As for the structure of the other carbons and the number of carbons will stay the same. So we can just redraw that over here. So we have 8 carbons here, and we just redraw them over here. Now, we're going to place the double bond exactly where the epoxide is, over here. And as for this methyl substituent, we're going to redraw it in the same carbon, in this case over here. Now as for a reagent, we're also getting an enantiomer, so we can use MCPBA. For this next example, notice that the substituents at either side of the epoxide are in different planes, as in this one is in a wedge and this one is on a dash. So when we want to redraw this ethyl group, we start by doing it over here. And once again, we can draw this line underneath the epoxide to remind ourselves that it came from an alkene. So we can redraw that over here. And because they're in different planes, we have to now draw this ethyl group in a trans conformation. So we can just redraw it over here. Once again, we're forming an enantiomer, so we can use MCPBA. For this next example, notice that the methyl and the phenyl group are in line conformations. So we can just redraw that. Once again, we can draw this line here to remind ourselves that the epoxide came from an alkene, and redraw that over here. Now the phenyl group will be in this side, and we'd redraw the alkene. Now as for this methyl and this hydrogen, notice that they're in the same plane, but we usually don't represent hydrogen, so we can just put the methyl group up here. Once again, we're forming an enantiomer, so we can use MCPBA. Now, ring openings reactions of epoxides occur regioselectively and stereoselectively. Stereoselectively, the reaction always proceeds with inversion of configuration. Regioselectively, under cationic conditions or acidic conditions, nucleophilic attack occurs on most substituted carbon. Under basic or anionic conditions, nucleophilic attack occurs on least substituted carbon, and that's because it's more accessible. So as we see here, when we're using an anionic nucleophile, it's going to attack the least substituted carbon. So in this case, it will attack this carbon. When it attacks this carbon, this bond breaks and it's given to the oxygen. Now, when we're doing workup with water, we add this hydrogen to this oxygen. So we'll have this as our answer. It's important to notice that we're also going to have inversion at this carbon. So how I like to remember that is that this oxygen will stay at any conformation it is in the epoxide. So in this case, it is in a wedge, so it's going to stay as a wedge. And because the nucleophile is going to attack from underneath the epoxide, it's going to get an inversion to its configuration, so in this case, it will stay as a dash. Now, when we're under acidic conditions and using neutral nucleophiles, it's going to attack the most substituted carbon. So in that case, it's going to attack this carbon, and this is the bond that will break and be given to the oxygen. Now, this would be our product, and once again, remind ourselves that because it's going to attack from the bottom, we're going to have this nucleophile on a dash conformation, and notice that this methyl group has changed to a wedge conformation. And once again, the oxygen will stay in a wedge conformation as it was here, and we're going to add the hydrogen once we do water workup. We're now asked to predict the products of the following reactions, show stereochemistry when necessary, and assume reactions end with workup. So first we're going to predict all the products, and then we're going to show stereochemistry. So the first thing we want to do here is notice under what conditions we're going to be working on. So NaSH is going to be working on anionic conditions. In this case, it's going to be attacking the least substituted carbon, and it's going to break this bond, and it's going to be given to the oxygen. Again, remember that's going to be attacking from the bottom upwards of the epoxide, so it's going to be on a different conformation than the epoxide. And as for the structure of these carbons are going to stay the same, so we can redraw that over here. Notice that we have 8 carbons, so we're going to redraw that over here. 1, 2, 3, 4, 5, 6, 7, 8. Now this SH group is going to have a different conformation than the oxygen, so we're going to draw it in a dash conformation. And this oxygen group is going to stay on a wedge, so we can redraw that over here. And this methyl group is going to stay on a dash conformation. Now because we're doing workup, we want to add the hydrogen to form this OH group. For this next example, notice that we're working with lithium aluminum deuterium. Deuterium is going to also be working under anionic conditions. So under anionic conditions, it's going to attack the least substituted carbon, it's going to break this bond once again, and it's going to be given to the oxygen. So we can redraw that over here, starting with this ethyl group. Now, this ethyl group will stay on the same conformation. Then we're going to redraw this carbon-to-carbon bond. And then we're going to draw the new carbon-deuterium bond down here. And notice that I'm using a line conformation because the epoxide was in a line conformation. So, and once again, the oxygen will also be in a line conformation. And because we're doing workup, we can just add the hydrogen up here. For this next example, notice that we're working under acidic conditions. And because we're working under acidic conditions, the first thing that's going to happen is protonation of the oxygen. So oxygen is going to want to grab hydrogen, making this positive, or a plus charge. The next step will be the methoxy group attacking the most substituted carbon because we're under cationic conditions. So in this case, the methoxy group is going to attack this carbon down here because it's the most substituted carbon. And notice that the phenyl group and the methyl group are already on line and dash conformation. So the only thing that's going to happen to them is they're going to be pushed upwards. So we can redraw this by redrawing the carbon-to-carbon bond first. Now we're going to add this new carbon to this methoxy group bond. And now the phenyl group is going to stay on a wedge, but it's going to be pushed upwards. Same as this methyl group is going to stay on a dash conformation, but pushed upwards. Now, as for our oxygen, it started as a line conformation, so we're going to leave it as a line conformation. And notice that it already has its hydrogen. Now, nothing happened to this carbon down here, so we can just leave it as a wedge for this methyl group, and we're not going to represent the hydrogen. For this next example, notice that we're using methyl magnesium bromide. So we're working with Grignard reagents. Grignard reagents are also under anionic conditions. So in this case, the methyl bond is going to be attacking this carbon down here. It's going to break this bond once again and be given to the oxygen. So we redraw this by drawing first the carbon-to-carbon bond. We can redraw this ethyl group in the same plane. And then we're going to draw this new methyl to this carbon bond. And once again, the oxygen is in a line conformation, so we can leave it at that. And because we're doing workup, we can add the hydrogen up here. For this next example, notice that we're also working under anionic conditions, since we have NaOH. So because we have anionic conditions, this OH group is going to be attacking the least substituted carbon. In this case down here, we're just going to break this bond, and it's going to be given to the oxygen. Now we redraw that once again, forming first the carbon-carbon bond, adding this new carbon OH group bond. And remember, because the oxygen is in a line conformation, we can just redraw that over here. And as for this methyl and this ethyl group, they're going to stay on the same conformation as in wedge and dash. So we can put them here. And let's not forget about workup, so we have to put the H here. So now we're going to be assigning configurations for the stereochemistry. So first of all, for stereochemistry, we want to look for steric centers. And steric centers are only where there are 4 different substituents. So the first thing we want to do is notice that here we have one steric center here and one steric center here. And now we have to assign priorities. We want to give the priority 4 to our smallest substituent. So in this case, this methyl group is going to be our priority number 4. And we also want it to be on a dash conformation. This OH group is going to be on our priority number 1. This carbon, because it connects to another carbon, which connects to an SH group, is going to be our carbon number 2. And this carbon, because it connects to other carbons, is going to be our priority number 3. So if we notice, the rotation goes this way, which is going to tell us it's an R configuration. For this next steric center, remember that we have a hydrogen here. I'm going to erase this number 2 really quick. And remember that we have a hydrogen here, which is on a wedge conformation. Now hydrogen will take our priority number 4, and this SH group is going to take our priority number 1. Now once again, because this carbon is connected to another carbon, which is connected to a OH group, is going to take priority number 2. So I'm going to put 2 right here and get rid of these. And this carbon, which is connected to another carbon, is going to take priority number 3. Now, we have to put priority number 4 in a dash conformation, so if we were to do that, we can just put a number 4 here and a number 1 here, and look at the rotation. So in this case, the rotation goes this way, which would tell us is an S configuration. But because we switched these two, it's going to actually be an R configuration. So this rotation, once again, is going to be S, but because we changed them, it's going to be an R. So both of these steric centers are R. For this next example, once again, let's not forget that there's going to be a hydrogen here. And let me go ahead and erase these. We're going to have this hydrogen here, so we're going to give that hydrogen priority number 4. This OH group is going to give us priority number 1. This ethyl group is going to take priority number 2. And this carbon, which is connected to deuterium, is going to take priority number 3. Now our least priority is already on a dash conformation, so we don't have to change anything. And if we notice, the rotation would go this way, which is telling us it's an S configuration. So the steric center right here is S. On this next example, once again, we have 2 different steric centers, one that would be formed right here and one that will form right here. For this first one, notice that the methyl group is going to take our priority number 4, and it's already on a dash dash conformation. This methoxy group is going to take priority number 1. This phenyl group has carbons connected to other carbons, while this carbon over here is connected to an OH group. So this is going to take priority number 2. So the phenyl group is going to take priority number 3. Now, at least priorities is already on a dash conformation, so we don't have to make any changes to it. And if we notice, the rotation is going to go this way. And it doesn't matter if we pass number 4. So this rotation is going to tell us it's an R configuration. For this next steric center, once again, let's not forget there is a hydrogen here, and it's already on a dash, so we can give that hydrogen priority number 4. This OH group is going to take priority number 1, and then this carbon to carbon bond, which is connected to other substituents, is going to take priority number 2. So we already have 2 here, so we're going to take that 2 into account. And then this methyl group is going to take priority number 3. Now, once again, if we see the rotation, it's going to go this way, which is going to tell us, once again, that it's an R configuration. So both of the steric centers are R. For this next example, notice that we do not have a steric center, since this side is the same as this side, and we need 4 different substituents. For this last example, notice that we have, once again, a steric center right here. And in this case, this OH group once again is going to take priority number 1. This methyl group is going to take priority number 4. And then this carbon is connected to an oxygen, so this is going to give us priority number 2. And this carbon that is connected to another carbon is going to give us priority number 3. So if we notice, once again, we have to change these two because we want priority number 4 to be on a dash. So if we were to do so, we're going to put 4 here and 3 here. We don't take these two into account. And see that the rotation goes once again this way, which will tell us it's an R configuration. But because we switch these two, it's actually going to be an S configuration. It is now asking us to fill in the empty boxes with the proper structures or reagents. So in this first example, we're given the starting material and the product. So notice that we start with an epoxide and now we don't have one, so it must have been a ring opening. And notice that it attacked the least substituted carbon. So if it attacks this carbon, this bond is going to be the one that's going to be broken and given to the oxygen. So we're going to be working under anionic conditions. And what we're going to be adding is this alkene group. So as we used here, we notice that we can use Grignard reagents and they are in anionic conditions. So that's exactly what we're going to use. So we're going to draw this alkene plus the Grignard reagent. And let's not forget about water. For this next example, we have to come up with a product. So LAH is going to be adding hydrogens to this epoxide to form a ring opening. But notice that we're going to be working under anionic conditions. So under anionic conditions, it's going to attack once again the least substituted carbon. It's going to break this bond and it's going to be given to the oxygen. So nothing happens to this ring here, so we can redraw that here. And put this ethyl substituent up here. And now remember that the epoxide was here, so we're going to add a hydrogen to this carbon here. Now as for this oxygen, it's going to be in the same carbon here. And because we're doing workup, we can put the hydrogen there. We're now given the reagent and the product. And notice that we're going to be working under cationic conditions, so acidic conditions. And that over here, even though as they kind of look if they were cis, they're actually on the same plane since both of them are wedge. So it means that the epoxide was symmetrical or cis to each other. So we can redraw this methyl group. Once again, we're going to put this carbon to carbon bond and redraw this other methyl group. Remember, because something must have attacked it from bottom up, this methyl group was pushed upwards. So we can redraw the methyl group over here. And not forget about our epoxide. For this next example, notice that it seems as nothing happened to it once again. So what's going to actually be happening is we're going to be adding a hydrogen. But we have to notice what would happen if we attack under anionic or cationic conditions. So under anionic conditions, we're going to be attacking the least substituted carbon, in this case up here, and it's going to be breaking this bond, and it's going to be given to the oxygen. And that would give us a methyl group with an OH group. So that's exactly what we want here. So something that it's going to contain hydrogens, as we use right here, it's going to be LAH. And it's also going to be under anionic conditions, so that's exactly what we're going to use here. Now this last example is a little bit more tricky. If we're using NaH, the first thing you want to do is notice if we're going to be under anionic or cationic conditions. But here, if we were under anionic conditions, it will attack this carbon and break this bond. But that would be erroneous. When we're using NaH, the first thing that's going to happen is we're going to deprotonate this hydrogen here. So if we deprotonate this hydrogen, this oxygen becomes a nucleophile. And it's the one that's going to be attacking the least substituted carbon and breaking this bond and giving it to the oxygen. So in this case, it will form a ring. And the important thing to do when we're forming a ring is count the number of carbons. So in this case, we have 1, 2, 3, 4, 5 carbons. So we redraw this by drawing first the oxygen and draw the 5 carbons to it. So 1, 2, 3, 4, 5, and the carbon. Now, we don't have to forget about this substituents here. So this methyl group, if you notice, if there was a bond here, if oxygen was here and it made a bond here, it's in carbon number 1, carbon number 2. So 1, 2, and we can redraw here the methyl group, and nothing's going to happen to it, so we can redraw it in a wedge conformation. And as for this oxygen, notice that we already have line conformation, so it has to be on a wedge conformations. So we can redraw this oxygen here. And let's not forget about the workup, so we can draw the H there. We're now asked to propose a synthetic strategy for the following transformations. Show only intermediate products to show our thinking, and to remember to use all the reactions we have learned up to now. So there are different methods of how we can treat these type of problems, but how I would do it is by looking at every single structure, and notice that it goes from this to this, from this to this, and from this to this. Now, we can do everything in a forward direction, but we can also use retrosynthesis, where we see the last product and think how we can get from here to here. So in this case, notice that we're forming an epoxide, and that it came from an alkene. So a reagent that we have learned that makes alkenes into epoxides is MCPBA. That should transform this alkene into this epoxide. Now again, we're looking at this alkyne and this alkene. Notice that the only thing we need is to add hydrogens in order to get rid of a pi bond. And that we're going to have to, and the alkene is going to be in a trans conformation. So to do so, we can use a reagent such as NH3 liquid. Now here, it might be hard to think of a way to come up just by looking at these two structures, how to get from here to here. But here, notice that we can add bromine plus heat to it. If we add bromine plus heat, we should get this intermediate. Now what we want to do is get rid of the bromine with a base, and any base should do so, but I like to use bulky bases. And that would form an alkene right here, giving us this intermediate. Now notice that we want to add more carbons to this terminal side of the alkene. So to do so, to add something here, we want to do it in an anti-Markovnikov fashion. And to do so, we're going to have to use peroxides. So we're going to want to add another bromine here. So we can use HBr, and not forget peroxide to give us this intermediate. Now, we're going to have to add this structure in order to get this product. So to do so, we want to use or think about Grignard reagents. So first we want to add or make this into a Grignard reagent by just adding magnesium. Now that the Grignard reagent has been prepared, we can simply add this alkyne. To enlarge the carbon structure. And we're going to want to follow that with water. And that's how we get from this compound all the way to this compound. For this next synthetic problem, notice that we have the same starting material as before. So we're going to have to follow a similar pathway. And once again, we're going to be adding onto this side, onto this carbon to get this product. Now, we can start this by doing a little bit of a retrosynthetic strategy, where we come up with what was before this final product. So as we can see, this seems similar to a ring opening, so we can assume it came from an epoxide. Notice that we're adding to the least substituted carbon, and that what we're adding is this methoxy group. So if we were to redraw this, we can redraw it like this. Now, because we're going to add this methoxy group, we can use something such as MEOH followed by water. Now, once again, remember that epoxides are made from alkenes. So if we were to move one step backwards and make this into an alkene, we would have this intermediate. And something that will transform this alkene into this epoxide is something such as MCPBA. Now we can go back to the starting reagent. So once again, as I said, we have the same starting reagent as before, so we can follow a similar pathway. So something that we're going to want to do first is add bromine once again. So if we were to add Br2 plus heat, we would get this intermediate. Now we want to get rid of that bromine, so to do so, we're going to use a base, and I like to use bulky bases for some reason. And when we use a bulky base, we'll get this intermediate, where we're going to form an alkene right here. Now remember, we're going to have to go from here, not to here anymore, but to here. So to do so, we're going to notice that we're going to add these two carbons. And one way we learn how to do it over here is by using Grignard reagents. But before that, we're going to have to add this in an antimicrobial fashion. So a reagent that will do so, once again, is something such as HBr, as we did right here, and a peroxide. This should give us this intermediate. Now we want to take from this intermediate to this product, or to this intermediate. So to do so, once again, we're going to follow Grignard reagent method. So we're going to add magnesium, which would give us this intermediate. And we can use an alkyne again and reduce it into this alkene. So once again, we want to use this alkyne followed with water to give us this intermediate. Nope, we don't need this extra. So, and finally, a way to get from this alkyne to this alkene is by reducing this by adding hydrogens, and something that will do so, and we don't care if it's trans or cis. Once again, we can use NaNH3 liquid. For this next synthesis strategy problem, once again I'm going to be using a retrosynthetic approach, where I see this final product and think, what must have this come from? If we see here, this looks similar to a ring opening of an epoxide. And if it came from a ring opening, it means that something must have attacked on the least substituted carbon in order to have this OH group in the most substituted carbon. So because it's going to attack the least substituted carbon, it means that we're in anionic conditions. And a reagent that is in anionic conditions and can form the ring opening is something such as the methyl group with a Grignard reagent. So if I were to redraw this as an epoxide, it will look similar to this. with this methyl group attached in this carbon. And once again, because we're in anionic conditions, something such as a Grignard reagent with this methyl group followed by water for the protonation of this oxygen could work. Now, we see this epoxide and we can think, what do we know that epoxides come from? And as we know, epoxides come from alkenes, such as the one we have here. So from here, in order to get from here to here, all we need is a reagent that makes alkenes into epoxides. And a reagent that turns alkenes into epoxides is MCPBA, as we have learned. So that would give us, well, that would take us from here to here. Now, it might be a little bit more difficult to think what was before this compound. So now I'm going to be moving on this starting material. So the first thing we're going to want to do is see what changes. So we're going to be adding carbon bonds on this side of the carbon. So first we're going to need to add a bromine to this starting material. And to do so, all we need is Br2 plus heat. That should give us this intermediate. Now, once again, we're going to want to add this structure. So to do so, we can just prepare this as a Grignard reagent. And to do so, we're going to have to add magnesium to it, which would give us this intermediate. And now think, now that we have a Grignard reagent, how can we make this into this? So if we use something such as an ketone, would give us the same number of carbons we need, plus an extra methyl group. But if we use something such as an aldehyde, we would get something similar to this. So if we use an aldehyde plus water, we will get this intermediate. Now notice that from this compound to this compound, all we need to do is get rid of this OH group and form an alkene right here. And to do so, all we need is to protonate this OH group to make it a good leaving group. So something that could do that is H3O+. We're now in the last synthesis problem. So it's telling us that we can only use reagents that contain 3 carbons or less for the following synthesis. So the first thing we want to do is notice that the alkyne are present in both the starting and the final product. So if we notice, this carbon-carbon bonds are going to be added on this side of the alkyne. So this whole structure is going to be added on the right side of the alkyne. So the first thing we're going to want to do is remember that the alkyne has a hydrogen right here, and that we're going to need to deprotonate that hydrogen. To do so, we're going to use NH2, and that should give us this intermediate. Now this has been converted into a nucleophile. Now, if we see this part right here, we can think of it as a ring opening. So if we were to use something such as an epoxide, this nucleophile is going to attack this carbon right here, and this bond is going to break and give it to that oxygen. And we will end up with this intermediate. I'm going to redraw it like this, just so it looks more as the side product. Now, we're also going to need the H2O in order to protonate that oxygen. So notice that all we're missing is this structure right here. But to do so, we're going to need to deprotonate this hydrogen, and that is not likely to happen. So instead, what we're going to want to do is think of this structure right here. That's going to be added. Now, we need to turn this hydroxy group or alcohol into a good leaving group. To do so, we're going to tosylate the alcohol. So we're going to use TsCl, followed with pyrimidine. Now, since we're tosylating, we'll get this intermediate. Notice that the alcohol is now a good leaving group, since we tosylate it, and that all we need is a nucleophile that will attack this carbon to get rid of this group. So we can literally just use this. So we're going to use sodium with this compound, or this structure, and this will attack this carbon right here, which will break this bond, and we should end up with this final product. And that is our desired product. Thank you so much for following along, and good luck on your OChem series.